So what we're doing here is we're going to prove that 5 to the power of n is divisible by 4 for all n and n. Now, 5 to the power of n, if we were to put this into a table format, for instance, okay, and we were to say mode table, and we said 5 to the power of x, 5 to the power of x minus 1, okay, and then we say, I don't know, start at 1, end at 10, okay, and step of 1. Now what we can see here is the numbers produced: 4, 24, 124, 624, 324, 1000, 15,624, 78,124, 39,624. They're all divisible by 4. You can check any of these numbers and they'll all divide by 4. Now what we want to prove is that this pattern will continue on forever, and in order to do this we're going to use a method called induction, okay? So induction is what we're going to use. So what we do first in induction questions is we're going to test for n equals 1. Okay, so the test for n equals 1, what we're going to do is we're going to say step 1. Sorry, excuse me. So step 1. Okay, so what we're going to do is 3 steps. Okay, so step 1 is test for p of 1. So we put in p1, and we're basically saying that p of n is 5n minus 1. So p of any number, replace n with that number. So p of 1 is 5 to the power of 1 minus 1, which gives me 4. Now 4 is divisible by 4. Hence p of 1 is true. Now what this means is that when you replace n with 1, the answer is 4, and 4 divided by 4 equals 1. So that means that p of 1 is true. Now step 2 is assume p of k is true. Okay, so assume p of k is true, which equals 5k minus 1, and assume it's divisible by 4. Okay, and then step 3 is to test p of k plus 1. Now p of k plus 1 equals 5k plus 1 minus 1. And you want to see that if this is divisible by 5. Now using your power of indices, you're going to put down 5 to the power k plus 1 equals 5 by 5 to the power k minus 1. Okay, you're going to change this number 5 in the brackets here into 4 plus 1 to the power of 5k minus 1. Now what you're going to see here is that we're going to separate this out into 2 parts. It's going to be 4 multiplied by 5 to the power k, and then it's going to be 1 times 5 to the power k. Now 1 times 5 to the power k is in fact 5 to the power k, so we don't need to worry about that there. Okay, and then what we get is 5 to the power k, and then we have minus 1 here. Now this part here, 4 divided by 5 to the power k, is divisible by 4. And this part is divisible by 4 by p of k. It's assumed divisible, because look guys, we've actually made p of k back out of it, and we assumed that p of k minus 1 is assumed divisible. Now guys, what this means here is that hence if p of k plus 1 is made up of a divisible part a part that's divisible by 4 and another part that's divisible by 4, it means that hence p of k plus 1 is true if p of k is true. So hence p of k plus 1 is divisible by 4 if p of k is divisible by 4. And then you say hence p of n is true via induction. Okay? Now let me tell you what that means, okay? If we go back to the start and we said we've proved p of 1 is true, okay? If we were to say k represents the number 1, okay, and what we then can say is that p of 1 is true. If p of 1 is true, hence this part here will be divisible by 4. This means that p of 2 is true. And then you can start back at the start saying if p of 2 is true, then it goes up, then p of 3 is true, and it keeps going and going and going. And that's how this induction works. Okay, we try another one now. Okay, so once again, 3 steps here, okay? So, 4 to the power of n minus 1 is divisible by 3 for all n element n. So this means n is 1, 2, 3, all the way up, and we have to prove that it works for all numbers, okay? So, what we're going to do with this one is, we're going to say p of n equals 4 to the power of n minus 1. We want to prove it's divisible by 3 for all n element n. Okay, step 1 is find out if p of 1 is true. So p of 1 equals 4 to the power of 1 minus 1. That equals 3. 3 divided by 3 equals 1. Hence, p of 1 is true. Okay. Step 2. We're going to assume p of k is true. So p of a random variable k is true. So if p of k is true, then p of k ends up to be 4 to the power of k minus 1. And it's assumed divisible by 3. Okay. Now, next part 3 is to test p of k plus 1. So step 3 is to test p of k plus 1. Now what we do here is we say p of k plus 1. We replace k with k plus 1, so it's going to be 4 into k plus 1 minus 1. Now I'm looking to make 4 to the power k minus 1 out of this, okay? So what I'm going to get is I'm going to break this up, and I'm going to get 4 to the power 4 times 4 to the k minus 1. Now I'm going to break this 4 up into 3 plus 1 4 to the k. It's always going to be plus 1, because what we got to do here is we got to separate out. So it's going to be 3 times 4 to the k. And then 1 times 4 to the k is simply 4 to the k minus 1. And we can once again see that this part here is divisible by 3. Because if you're multiplying by 3, you're divisible by 3. And then this part here is assumed to be divisible. So assumed to be divisible by p of k. So this is p of k plus 1. Now p of k plus 1 is now comprised of 2 different parts that are divisible by 3. So what we can say is hence p of k plus 1 is divisible by 3 if P of k is divisible by 3. Hence, P of k plus 1 is true if P of k is true. Hence, P of n is true. Now guys, imagine this, alright? Imagine k equals 1, and we know that P of 1 is true. And that's the first test we did. Now, by that logic, k of plus 1 has to be true because P of 1 is true. So that means P of 2 is true. And then we can, by the same logic, if P of 2 is true, P of 3 is true. This is not part of the answer, this is just explanation. So basically, by proving P of 1 is true, then assuming the generic P of k is true, and then using this P of k to prove that P of k plus 1 is true, by having P of 1 true, then P of 2 knocks on from that and it also must be true. Okay? All through the variable k. Okay, so we want to make sure that P of n equals 13 to the power of n minus 5 to the power of n is divisible by 8 for all n element n. So n starting 1, 2, 3 all the way up. Now, what we're going to do is step 1. We're going to try for P of 1. P of 1 equals 13 to the power of 1 minus 5 to the power of 1 equals 8. 8 divided by 8 equals 1. Hence, P of 1 is true. Step 2. Assume true. So I'm going to assume it's true for P of k equals to 13k minus 5 to the power of k. And now I'm going to test step 3. I'm going to test P of k plus 1. And P of k plus 1 equals 13 k plus 1 minus 5 k plus 1. So what we're going to do here, guys, is we're going to convert this P of k plus 1 into 13 by 13 to the power of k, and then the other part is going to be minus 5 times 5 to the power of k. Now what you always do is you break the bigger number, the 13, the bigger coefficient if you will, break the bigger coefficient into the smaller coefficients. So we're going to break 13 up into 8 plus 5. Okay? So what happens here, we're going to get 8 plus 5, 13 to the power of k, minus 5 times 5 to the power of k. And look what happens here. So we're going to get 8 times 13 to the power of k, plus 5 times 13 to the power of k, minus 5 times 5 to the power of k. And what happens when we break the bigger number and the small number, we can factorize out 5. So we have 5 bracket 13 to the power of k minus 5 to the power of k. And we have 8 times 13 to the power of k. Now, this part here is divisible by 8, because 8 divided by 8 equals 1. Okay, this part here is assumed divisible by P of k. So assumed divisible by 8 by P of k, because remember, look, it's the same thing as P of k. Here it is here. Okay, so therefore, hence P of k plus 1 is divisible by 8 if P of k is true Hence, by the principle of mathematical induction, so principle with a LE, so principle of mathematical induction, P of n is true. Okie dokes.